Welcome to Lecture 6.2, Semi-Infinite Domains and the Reflection Method. In this lecture, we will solve the heat and the wave equation where x is restricted to the positive real numbers. The technique is quite simple. We will take the initial condition and we will extend it to the entire real line, either by making it to an even function or an odd function, much like what we did with Fourier series. At this point, we've turned our PDE into something defined on the entire real line, and we know how to solve this. That's what we saw in the previous lecture. Let's get started. We'll begin with the heat equation with Dirichlet, or type 1 boundary conditions. That is, the temperature is going to be fixed at 0 at the one endpoint. So let me draw a picture of this. Suppose we have this half-infinite bar here, and at the endpoint we have temperature fixed at 0 degrees, and let's put an initial condition on this. Let's say it's something like this. It doesn't actually have to be 0 at the endpoint because it's defined only for positive values of x. So this is u of x 0 equals h of x. So to solve this, we will extend this function, h, to be an odd function defined on the entire real line. So in other words, we will make this continue in both directions, and then we'll define this. So let's basically do the odd extension. So I'm going to call this h naught of x, 0 for 0, or the O for odd. And then because it's an odd function, we have to define it to be 0 at the origin anyways. So motivation for why we're doing this, let's recall we saw earlier with the heat equation when we had a bar. Actually, let me draw it like this. So we had a bar defined on 0 to L. So we had a finite domain, and suppose this was our initial condition, u of x 0 equals h of x. So to solve this, we ended up getting an infinite series involving sines and cosines. And so if we had these same old type 1 boundary conditions where the endpoints are fixed at 0, then we extended this function to be odd. We took the odd extension. Well, why odd and not even? Well, because we had no choice. These things being 0 means it has to be a sine wave. So for example, this might be that x L minus x function. I don't mean it to be a sine wave. It's that one that we've seen a lot before. So for this equation, we took this odd extension and we solved the PDE. We really did is solved it on the entire real line, and then we just took the restriction of that solution to 0L. And that's exactly what we're going to do here. We are going to take this function, take the odd extension. Here's the formal equations of the odd extension. And now we have a function defined on the entire real line. It's not periodic. However, we know how to solve the heat equation on the entire real line. We did that in the last lecture. It involves that Gaussian. So one quick comment. This is example 1. We'll do example 2 where we have the other kind of boundary conditions. So later we will do the type 2, ux0t equals 0. So here's a picture of what that looks like for the bounded case. Recall that if we have the same initial condition, but we had this condition, then we had to take the even extension. So not surprisingly, if this condition up here, if this were an x, we have type 2 boundary conditions, then we do the same thing here, but instead of an odd function, odd extension, we make it an even extension. And we'll do that later. More formally, we are going to turn this PDE on a semi-infinite domain into one on the entire real line. Now we should probably call it a different function, so we're going to call it v instead of u. And the initial condition, v of x 0, is just this odd extension, h naught of x. Recall from the previous lecture that we have a very nice formula for the solution to this Cauchy problem. Namely, it's the integral over the whole real line of the initial condition, h naught of y, times g of x minus y and t with respect to y, where g is this Gaussian, this bell curve. So we're basically done. Nothing really more to do, right? Well, turns out we can simplify this a little bit. It's not too surprisingly, because of the symmetry involved. We don't need to write this as an integral from negative infinity to infinity, and this extension h naught. What we want to do is we want to write it in terms of this original function h of x, which is just defined on 0 to infinity. Okay, let's get started. So to solve the heat equation on the semi-infinite line for a general initial condition, and we have one boundary condition, the first thing to do is to turn this into a function of v. So vt equals c squared vxx, where v is going to be defined on the entire real line. And then let's skip to the initial condition. V of x0 equals the odd extension, so I'm going to call that h naught of x. So let me sketch what this looks like. So here's the real line. At x equals 0, the original temperature is fixed at 0 degrees. Here is, let's say this is u of x0 equals h of x. So we take the odd extension. And before we go any further, let's think about what happens as time gets larger. So for a larger value of time, so this is going to flatten out and do something like this. And then for larger t, it's going to get even flatter. And of course, in the long term, it's going to approach 0 degrees everywhere. Now, at the origin, the temperature is going to be 0 for all time t. Hopefully you can see this. So I don't really need this extra condition. I don't need to turn this boundary condition into one in v. And it doesn't really belong there anyways, because once I've extended it to the entire real line, this is no longer the boundary of anything. So we're just going to omit it and then solve this. Now this is something that we know how to solve. We did this in the last lecture. Recall that v, let me write this h naught of x over here. Okay, so v of xt, the solution here is the integral over the entire real line of the initial condition h naught of y g of x minus y t dy. So of course this is generally not going to be differentiable at the origin, so we have to break this up into two pieces. So the first piece, integral from negative infinity to 0 of h naught of y times g of x minus y t dy plus 0 to infinity h naught of y g x minus y t dy. Now let me remind you that I could stop here, our first line. That is the solution. There's nothing wrong with that. It's just nicer if we could write things in terms of the original functions, and we will exploit symmetry to do this. So we're just going to simplify this a little bit. Okay, so recall that the odd extension for negative values of x, h naught of x equals negative h of negative x. So right away, this h naught of y equals h of y, because we are only on positive values of y here. And then for negative values of y, this h naught of y, we can write it as negative h of negative y. So I'm going to rewrite this. I could do this all at once, but I'm going to do it step by step so you can see where, because it's really easy to make a mistake as well. So this is negative integral from negative infinity to 0 of h of negative y, g of x minus y, and then everything else is going to be the same, dy, and then the next integral is going to be the same, 0 to infinity, though I'm going to make this h of y, so now everything's in terms of the original function, g of x minus y t dy. Now, this integral goes from negative infinity to 0, but I want to show you how we can simplify this. So I'm going to draw just an arbitrary function, call it g of x, or maybe if you want to call it g of y. Yeah, let's do that. G of y. And if we want to reflect this across the, I was going to say y-axis, but across the vertical axis, then that function is, of course, g of negative y. So this is g of negative y. So notice how these two functions are related. They're just reflections of each other. And so if we take the integral of one of these, so let's integrate from negative infinity to 0 of g of y, that's the area under the curve. Well, of course, that's just going to be equal to the area under the curve in this region. So that's the integral from 0 to infinity of g of negative y dy. Okay? So given that, I can rewrite this integral. Instead of going from negative infinity to 0 of h of negative y, I can make this so that the negative sign still persists. I'm going to change this integral from 0 to infinity of h of y. So now I have to change all the y. I have to flip the signs of all the y's, and there's another y in there as well. So just to highlight, there's a negative y there, and there's a negative y there. So this is g of x plus y t dy. So again, this picture should provide motivation for why we did that. If you look at it symbolically, it's so easy to get confused. And then I'm going to keep the second one exactly the same. So I'm not going to change a thing in the second integrand. And now I can combine terms. So look what I have here. I have an integral from 0 to infinity. I have an h of y here. And then I got to factor out, let's see, I have a positive g here and a negative g here, though the arguments are different. So h of y times a g of x minus y t minus g of x plus y t dy. And that is the solution we seek. That is precisely the solution to the heat equation on the entire real line, although we can take just like we did for bounded domains, we can just restrict this to the positive reals, and we get our solution on the half real line. Our next example, the next slide, is going to be the same thing, except we have Neumann boundary conditions instead of Dirichlet. So instead of this boundary condition here, the temperature being fixed at 0, we are going to make this ux 0 and t being 0. So let's think about how that's going to change things. So first of all, instead of the odd extension, we're going to have the even extension. So let me sketch that like this. And then we still get the same solution, except this is going to be even. So this the even extension, where h of negative x equals h of x. And so that's going to change this step right here. So the even extension is going to, instead of making this negative h of negative y, it's going to make it positive h of negative y. And everything else is going to be the same. So we get down here, and the only difference for the type 2 boundary conditions is this negative becomes a plus, plus that becomes a plus, and that's it. So the next slide, I'm actually going to do this in a few more steps so you can see it formally. Here is formally the PDE that I solved at the end of the last slide. That is the boundary and initial value problem for the heat equation on the semi-infinite line with Neumann conditions. So let me sketch what this represents first. So suppose we have a semi-infinite domain, and the initial, well, before I get there, Neumann conditions means that the endpoint is insulated, so heat cannot enter or leave. So suppose the initial condition looks like this: h of x equals u of x 0. So intuitively, the heat will dissipate and spread out. So over time, it will decrease, and let me use a different color after this, and approach the average value. Now, you got to be careful with average value because we're on an infinite domain, and of course that that there's technicalities where that might not exist depending on the function, but we're not going to deal with that in this lecture or in this class. Intuitively, you know that this thing should spread out and get as flat as possible. So the even extension of this is defined as you would expect. And I think it's easier just to look at the picture. So let's say that the y-axis is there. So the hardest part, of course, is drawing it. And then the solution curves for a larger t, like these two here, are going to look like this, and then this, and so forth. Okay, so let's solve this. And of course, I basically already told you what it was, and the steps are almost the same. So I'm going to go through them quickly. So we're going to write this as a PDE in V. And of course, we don't need this boundary condition because when we extend V to the entire real line, there's no boundary anymore. And that becomes forced anyway. So HE of x. Okay, so we have a solution to this from the previous lecture. It is the integral over the entire real line of HE of y times g of x minus y t dy. Now we need to break this into two integrals because in general this is not going to be differentiable at this point. So we go first of all from negative infinity to infinity of HE of y. I'm going to skip a step here. So HE of y, well, no I won't. Let's just be careful because it's easy to mess up a sign. So HE of, I'm supposed to go negative infinity to 0, HE of y, g of x minus y, same thing. And then we're going from 0 to infinity of the same thing, HE of y times g of x minus y and t. Next, recall that when y is positive, this is equal to h of y, and when y is positive, this is equal to h of negative y. Now the difference in the previous lecture was we had a negative out here, and that's the only difference in this entire problem. So here we're going to go from negative infinity to 0 of h of negative y, g of x minus y t dy, and we're going from, and then everything is the same except this is an h of y, g of x minus y t dy. And finally, recall, it always helps to draw a picture that for any function g of y, we reflect it across the vertical axis. That is g of negative y. So the integral from negative infinity to 0 of g of y is equal to the integral from 0 to infinity of g of negative y. So I can turn this first integral into one from 0 to infinity, but I just have to make all of these y's, I have to flip the sign. So I have to make them from negative to positive. So h of y, g of x plus y t, and then the next integral is exactly the same, nothing changes. And so we can put this together. We can write this as one integral from 0 to infinity of h of y, and then we can factor out and we get g of x minus y. Oops, x, I got to put a t in there. And then plus g of x plus y t dy. And that's it. Remember, the only difference to the previous part where we had Dirichlet conditions and the odd extension is that positive sign in the last slide was negative. Next, we're going to solve the wave equation on a half-infinite domain with type 1 or Dirichlet boundary conditions. So let me draw a picture of this. So here's half-infinite domain. We have a wave like this. You can think of it like maybe like an infinite string, or maybe better, you can think of it like waves that are traveling in like a one-dimensional swimming pool. So we need to make this function odd. This is the initial displacement. U of x 0 equals f of x. So the odd extension of f is defined to be, so it's, again, of course, f of x when x is positive. It's 0 when x equals 0, and it's negative f of negative x when x is negative. Similarly, we need to specify the initial velocity of the wave. That's built into the boundary and initial value problem. So g, or the odd extension of g, is g of x when x, it's the same thing, x is positive, 0 when x is 0, and negative g of negative x when x is negative. Okay, so we need to turn this PDE into one defined on the entire real line. So we use a function v, so vtt equals c squared vxx as before. We can ignore the boundary condition because it goes away once we extend it on the whole real line, and it is implied anyways. Now recall what's going to happen is these will be traveling waves that are going to go in that direction. Well, actually, both of these are going to be traveling waves, and they split up, and half goes to the left and half goes to the right. In other words, we know how to solve this. We did this in the previous lecture. So our two initial conditions, writing in terms of v, so v of x 0 is just the odd extension of f, and the initial velocity, oops, that should be a v, not a u, vt of x 0 is g naught of x. Okay, and this solution that I've sketched, where the wave splits up and half of it goes in one direction, half goes in the other, we have a solution for that, or we have a formula for that. So del Ambert's solution is, so let me write this down, del Ambert's formula, this is what we did in the previous lecture, says that v is 1/2 times the initial, well, let's say f naught of x plus ct plus f naught of x minus ct. So this represents the initial wave, half of it going to the left and half of it going to the right. Now there's going to be some, we got to be careful, there's going to be some interference. Well, I'm just going to wait and show you. So let's keep going. Plus 1 over 2c times integral from x minus ct, x plus ct of the odd extension of g ds. Okay, so this is the solution to this initial value problem. However, we got to be careful because we have done this odd extension, but this odd extension, this wave is going to travel both directions, and it's going to interfere eventually, for long enough, it's going to interfere with the original wave, and we don't want that. So see what I mean by that? If we wait long enough, this artificial wave that we put is going to go this way, and it's going to be interfering with this here. So here's what I'm going to do. I'm going to draw a picture of the positive reals. So this is x equals 0, and this is, say, x equals ct. So when this interference happens is dependent on whether x is less than ct or x is bigger than ct, because that's the c is the speed of the wave. If you're having trouble visualizing this, just look at this picture. So there's going to be two cases. So case 1 is going to be when x is bigger than ct. Let's just focus on that now. When x is bigger than ct, then all of these quantities, x plus ct, x minus ct, both of these quantities are positive. And moreover, these quantities appear in the integral. Those are positive. So in this case, let me write this down. So case 1, when x is bigger than ct, then f naught of x plus ct equals f of x plus ct. Now we also have f naught of x minus ct equals f of x minus ct. And on this interval from x minus ct to x plus ct, so both of these are positive, and so on this interval, so g naught of s equals g of s on the interval x minus ct to x plus ct. Okay, because that interval is going to be entirely contained in the positive reals. So in this case, when x is bigger than ct, this is our solution. Well, when I say if we get, I guess this is our solution, we can just get rid of these extensions, and the solution is v of xt is 1/2 times f of x plus ct plus f of x minus ct plus 1/2c. We can integrate from x minus ct to x plus ct, g of s ds. So we don't have to worry about anything. These things are just the original functions f and g. Things are a little bit different when we're in this region. So when x is, actually let me call this case 2. So I'll write it over here. Case 2, x is less than ct. Of course, x is positive. So x is between 0 and ct. So we got to be careful because now things like x minus ct here and here are negative. So we have to use the definition. So in that case, we need to use the definition of the extensions, and we got to write this f naught and this function here, or this thing, we got to write in terms of negative f of negative x. Okay, so let's be careful with that. So let's repeat what we just did here. So f naught of x plus ct, still x plus ct is still positive, of course, because x and ct are positive, so nothing changes. That's f of x plus ct. However, in this case, this argument is negative. So we have to say that f naught of x minus ct is negative f of negative this argument. So negative x minus ct quantity is ct minus x. Okay? And now we also have to deal with this integral, but I think it's easier to do that once we write down the integral. So I'm going to hold off on this here. Okay. So let's write down the solution. So v of x t is 1/2. Let me see how I want to do this. I'm not going to write this whole line down. I'm just going to modify this line. So this line here still holds, but I'm just going to eliminate. I'm going to write these f naughts in terms of f. So it's 1/2 times f of x plus ct plus, and now we got to be. This is going to change. That is going to become this. So plus, actually, I probably should say minus. So that's minus, let's make that a little darker, f of ct minus x. So that's simple enough. This thing just turns into this thing. Now, this integral, so this is negative, that's positive. So here's kind of a picture of of what this looks like in this case. So this is going to be x minus ct. This is going to be 0, and this is going to be x plus ct. Okay, so let's break this into two integrals, 1 over 2c. Let's go from, you can't stop me from breaking this into two integrals. X minus ct, that's going to be a negative number to 0 of g naught of s. And then 1 over 2c, we're going from 0 to x plus ct g naught of s ds. Okay. This integral, we can change this g naught to g because it's x is positive, and in that case g naught is equal to g. This one we have to be a little bit careful of. Now I'm going to go up in this upper right hand corner and away from everything, and let's draw a picture that you've seen before. So let's suppose we have a function. Now if you want to change variables and do the chain rule, you can change variables. You can let s be negative s and play with this, but let's see what's going to happen here, because it's personally I like to draw a picture and just use intuition. Okay, so let's suppose that we are integrating a function. So we have a function g of s, and suppose we're going to integrate it from a to 0. So here's a picture of that. Let's consider the function, because, and I'm saying that because on this region, this function here is going to be negative g of negative s. So to integrate that from in this region, we have to change variables. We have to, like, we can let t be negative s, and then, but it's so easy to mess up those limits if we do that. It's not as hard with a picture. So this is g of s, and g of negative s, again, looks like, I don't mean to draw these areas to be the same. That's just, I just want some part of it to be under, some part of it to be over. So say this is from, so this is, let's see what let me say this is from negative a to 0, and say this is from 0 to a. This is g of negative s. Although honestly, you know, let's put the negative in here. It doesn't matter, right, by symmetry. So I'm going to call this g of s, and that's going to be g of negative s. So notice that if we integrate from negative a to 0, g of negative s ds, that's this area here, is the same as this area here. So we're integrating now from positive 0 to positive a of g of s ds. However, I would still like to combine this into one integral, where we're going from the negative number to the positive number. So one thing I'm going to do, notice that what I want to do, I don't need to, but I'm going to rewrite this. You can't stop me from switching the order and saying this is a to 0 g of s ds. And I'm going to put, if I do that, I got to put a negative sign there. So if I want to, I can integrate in the opposite direction. I do this. Okay, so let's now work with this. So this integral, so first of all, I'm just going to put quotation marks here. Nothing here is going to change. Let's also deal with the second one, because this is easy. 1 over 2c, integrating from 0 to x plus ct, g of s ds. Again, when x is positive, g naught is just g, and here's the tricky one. And it's tricky because it's easy to mess up these little details. 1 over 2c. Okay, so we are now going to, so we got to substitute this g naught for negative g of negative s, right? So let me do that. well, I'm going to integrate. So I'm going to stick a negative g of negative s ds. But now from this argument up here, I can replace, if I want to, so I can go from here to here, whereas I can turn the negative s into a positive s. Let's do that. Negative s into a positive s. But to do that, I need to, going from here to here, changing the negative s to a positive s, changing the sign of g, putting a negative sign out in front. If I do that, a negative sign out in front makes that positive. And what I've done from here to here is I've switched the sign of this bottom limit from negative a to positive a. So we are going from, so this limit from this thing to its negative makes it going from x minus ct to ct minus x, which, by the way, is positive, smaller than this. So again, if you wanted to, you didn't have to draw this picture. You could have right from here, done this thing that I did, and then if you wanted to, you could have said let t be negative s and done a change of variables. But I like doing it by picture. I think it's harder to make a mistake. Now we can combine these two cases. So we can combine these two integrals because they're the same thing in here. And we're going from this lower limit to that upper limit. So to summarize, I'm going to write this as, so v of xt, let's write this together, is 1/2 from f of x. So now I'm just going to copy paste the same thing down here and combine these integrals. So it's 1/2 of times f of x plus ct minus f of ct minus x plus 1 over 2c from ct minus x to x plus ct of g of s ds. So this is what we get when x is less than ct in our original equation. And this is what we get. Oops, not that. Sorry. This is what we get down here. Almost the same. When x is bigger than ct. And physically this represents, when x is bigger than ct, that just means that the wave has not gotten there yet. So this wave here moving, this artificial wave that we had to add has not, we're far enough out here that this wave has not moved here to interfere. So the solution is simpler. Here we have to take into account the interference. Okay, so that's the wave equation on a semi-infinite domain. It's a little messier, but that's basically just in the simplification. As before, the first step we wrote down absolutely is a solution. We just wanted to simplify it more, but there just happened to be two cases. We'll conclude this lecture with a summary comparing the heat and the wave equations on a semi-infinite domain. So in all of these cases, what we do is we have the semi-infinite domain, and we have our initial function, our initial condition, possibly 2 if it's the wave equation, and we turn it into the odd extension, and then we solve that equation on the entire real line. And that's what we learned to do in the previous lecture. So for the heat equation, the integral is, or the solution is the integral from 0 to infinity of this heat kernel, or fundamental solution, g of x minus yt minus g of x plus yt times the initial condition integrated with respect to y. For the wave equation, we have two initial conditions, and what we get is basically D'Alembert's solution if x is bigger than ct. And for x being less than ct, we get D'Alembert's solution slightly modified due to the fact that we had to undo the odd extension of f and g. So these two negatives, or these two things are negative of what they were up here, and this lower limit is negative of this lower limit up here. Otherwise, everything is the same, and that's just due to the interference. Okay, so that takes us to the end of this lecture. In this lecture and the previous, we have seen how to solve PDEs on infinite and semi-infinite domains. There's actually another way to do this, and that's going to be the topic, the remainder of this section, and that's using Fourier and Laplace transforms. So recall that a Laplace transform takes a function of t to a function of s, and a Fourier transform takes a function of x to a function, let's write it, of c. And the key property is that these transforms take derivatives on the left-hand side to multiplication on the right-hand side. So for ODEs, we could solve differential equations by turning derivatives into multiplication, thereby turning ODEs into algebraic equations. So a Laplace transform, you saw this in your ODEs class, takes an ODE into an algebraic equation in S. So if we take a Laplace transform to a PDE in space and time, x and t, then what we're going to get is an ODE. The t is going to go away, so we're just going to get an ODE in x. Similarly, if we take a Fourier transform of an of a PDE in x and t, we're going to get an ODE. The x derivative goes away, turns into multiplication, so the only variable left is going to be t. So we're going to get an ODE in t. So that's what we're going to look at in the next lecture. Stay with us.